Good morning, children. In this video lecture, I am going to demonstrate transport network analysis connectivity. I have designed this lecture especially for the undergraduate students of post semester geography honors. I'll try to make it easy for you all. Hope you all will be benefited. The entire lecture is divided into three phases. In first phase, I'll try to give you fundamental idea of transport network and graph theory. The second phase is designed to give you some basic ideas related to graph theory. In third phase, the connectivity measures of transport network will be demonstrated. So let's start. First of all, we'll be talking about transport network. Transport network is the combination of two words, transport and network. So what do we understand by transport? Transport or communication is the movement of humans, animals and goods from one location to another. In other words, the action of transport is defined as a particular movement of a people, goods and ideas from a point A to a point B. Modes of transport include air, land, water, cable, pipeline and space. And on the other hand, network. Geographers defined it as a set of geographic locations interconnected in a system by a number of routes. Networks are highly complex spatial systems which is used to study transport network forms and structures, particularly how they change in time. Therefore, a transport network or transportation network is a realization of a spatial network describing a structure which permits either vehicular movement or flow of some commodity. Examples include but are not limited to road networks, railways, air, pipelines and power lines. In network analysis, networks are reduced to a level of graphs. Look at this two image. This is image of road transport network, and this road transport network is converted into graph. So now we will be talking about the fundamental concepts or ideas about the graph and graph theories. A graph is a symbolic representation of a network and of its connectivity. It implies an abstraction of the reality, so it can be simplified as a set of linked nodes. A precaution is essential in simplifying the network in a comprehensive, understandable graphic form because of topological properties of the transportation have to be considered and not the whole range of properties identified with any given network. Graph theory is a branch of mathematics concerned with the how networks can be encoded and their properties measured. It has been enriched in the last decades by growing influences from studies of social and complex networks. The goal of a graph is representing the structure, not the appearance of the network. The conversion of a real network into a planar graph is a straightforward process. Though the new approaches were pioneered by Garrison and Marble in 1962, the first geographical application was made by Kansky in 1963, who used various graph theoretic measures such as alpha, beta, gamma, cyclomatic number, eta, theta and pi index. Graph theory has found relevance in a variety of problems. The advantage of graph theoretic measures is that it provides the meaningful simplification or understanding and interpretation of the complex transport network. As we have talked earlier about a graph, simply a graph denoted by G is a set of vertices or nodes denoted by V connected by edges denoted by E. Thus, a graph is simply G is equal to V and E. Now we'll talk about vertex. What do you understand by vertex? Vertex, a node, is a terminal point or an intersection point of a graph. It is the abstraction of a location such as a city, an administrative division, a road intersection, or a transport terminals like a station, harbors, and airports. Look, these blue dots are the nodes. Now we'll talk about edge. An edge is a link between two nodes. A link is the abstraction of a transport infrastructure supporting movements between nodes. It has been a direction that is commonly represented as an arrow. When an arrow is not used, it is assumed the link is bidirectional. Look here, this green color, these are the links which joins the nodes. So now this is the image of the graph. Now we will talk about a subgraph. A subgraph is a subset of a graph. The number of subgraph is denoted by English letter P. Unless the global transport system is considered in its whole, every transport network is in theory a subgraph of another. For instance, the road transportation network of a city is a subgraph of a regional transportation network, which is itself a subgraph of a national transportation network. Now look at this image. Image A is image of planar graph, and B is an image of non-planar graph. So what do we understand by planar graph? Graph A is a planar since no link is overlapping with another, and graph B is non-planar since many links are overlapping. So simply, a planar graph where all the intersections of two edges are a vertex. Since the graph is located within a plane, its topology is two-dimensional. This is typically the case of for power grids, road, and railway networks, although great care must be inferred to the definition of nodes. Now we'll talk about non-planar graph in little bit details. A graph where there are no vertices at the intersection of at least two edges. This implies a third dimension in the topology of the graph, since there is the possibility of having a movement passing over another movement, such as for air and maritime transport. A non-planar graph has potentially many more links than a planar graph. Now look at this image. Here we'll be talking about cycle and circuit. Cycle, this is cycle and this is circuit. Look, cycle refers to a chain where the initial and terminal node is the same and that doesn't use the same link more than once is a cycle. A path where initial and terminal node corresponds is known as circuit. It is a cycle where all the links are traveled in same direction. Now we'll talk about connectivity. The connectivity of a network may be defined as the degree of completeness of the links between nodes. The degree of connection between all vertices is defined as the connectivity of the networks. The greater the degree of connectivity within a transportation network, the more efficient will that transportation system be. This connectivity can be measured in two ways. One is degree of connectivity, another is nodal connectivity or direct connectivity. The degree of connectivity can be measured by alpha, beta, gamma, cyclomatic number, and diameter by these indices. Now, degree of connectivity. The degree of connectivity of transport network is indicative of the complexity of the spatial order that imposes on the region it serves. The intensely developed network system should exhibit the greatest number of interconnections. Kansky in 1963 has studied the structure of transportation network, developed several descriptive indices for measuring the connectivity of the networks. I have already mentioned these indices are beta, gamma, alpha indices and cyclomatic number. Now, about cyclomatic number. Cyclomatic number is a different way of measuring connectivity. This is based upon the condition that as soon as the connected network has enough arcs or links to form a tree, then any additional arcs will result in the formation of circuits. Thus, the number of circuits in a connected network equals to total number of arcs minus the number of arcs required to form a tree, that is one less than the nodes or vertices. It may be written as mu is equal to E minus V plus P, where E is for edge, V is for vertices and P is for number of subgraph, unconnected subgraph. Look at this graph, look at this image. In graph there are 4 graphs and cyclomatic number is measured. Look here, in the graph A there are 5 nodes and 3 edges. What should be the cyclomatic number? E minus V plus P. E here, E is 3, V is 5 and P means number of unconnected subgraph is 2, so it is 2 and the cyclomatic number is 0. And look at this graph B. Here the number of nodes are 5 and number of edges are 5 and number of subconnected graph is unconnected subgraph is 1, therefore the cyclomatic number is 1. Similarly, you can find out the cyclomatic number of graph C. In the graph C, here number of vertices are 4 and number of edges are 5. 1, 2, 3, 4, 5 and number of unconnected subgraph is 1, therefore the cyclomatic number is 2. So now we'll talk about another index, that is the alpha index. It is the adjusted form of the cyclomatic number which evaluates the number of cycles in a graph, comparison with the maximum number of cycle. In other words, it is the ratio of the observed number of fundamental circuits to the maximum number of possible circuits. So it may be written as E minus V plus 1 divided by 2V minus 5. Here again there are 4 graphs, and in graph A I'll show you how to calculate the alpha index. Look, in the graph A there are 4 vertices and 3 edges. So first we have to find out the cyclomatic number here, and then this 2 into V minus 5, and that cyclomatic number should be divided by 2V minus 5, and this is the alpha index, and you can find out this alpha index of other graphs. Now we'll talk about beta index. It is the ratio of the total number of edges to total number of vertices. The formula is E divided by V. Look here in the graph A there are 4 vertices and 2 nodes. So as per the formula, number of edges are 2, that should be divided by number of vertices, and 2 should be divided by number of vertices 4, and beta value is 0.05. And similarly we can find out the beta value or beta index value of other graphs. Now gamma index. It considers the relationship between the number of observed edges or vertices and the number of possible edges or vertices. The planar graph In planar graph, the addition of one node increases the maximum number of edges by 3. This progression is true for any planar network of more than 2 nodes. So it is expressed as E minus E divided by 3 into B minus 2. Look here, in this graph A, there is 1, 2, 3, 4, 5 vertices, and there are 1, 2, 3, 4 nodes. And here, this is the way how to calculate the gamma index. Now, we'll talk about diameter. The index of measuring the shape of a network is diameter. It is very often considered as a weak index for measuring the transport network. Diameter is an index for measuring the shape of a network by counting the number of edges in the shortest path between the most distant vertices. The length of the shortest path between the most distanced nodes of a graph. It measures the extent of a graph and the topological length between two nodes. Look at this graph. So here this is the data matrix, and total number of nodes are 7. So the data matrix should be 7 into 7. Here this is the vertices 1 to 7. Here it is 1 to 7. Now we'll try to find out the symbol distance. How to find out? We have to find out it following the shortest path. So now from node 1 we'll start. Look at node 1 to 1, there is no edge. No edge is required to reach from 1 to 1. So that's why it is 0. And from 1 to 2, to reach from 1 to 2, we need only one edge. That's why it is 1. And from 1 to 3, we need only one edge, so it is 1. Now from 1 to 4, look, we have two routes to reach 4 from 1. One route is this, another route is this. Now we have to find out the shortest path. Like shortest path means which the path which we need to cover the minimum number of edges to reach the destination. Look here, from 1 to 4 in this side, 1 and 2 edges are required. In this direction again it is 1 and 2. 2 edges are required. So in both sides it is same. So we can write 2. From 1 to 5, look here, 1 to 5 we need 5. In this direction if we move, 1 edge, 2 edge, 3 edge, 4 edges are required to cover. In this direction if we move, 1 and 2 edges are required, and in this direction if we move, we need 2 edges to cover. So following the shortest path matrix, we found 2 edges required to be covered to reach from 1. So that's why the value is 2. Now 6, look here, from 1 to 6 we have 3 route. In this route if we want to reach 6, then we need to cover 1, 2, 3 edges. From this side if we want to reach 6, destination 6, then again 1, 2, 3 edges are required to cover. But in this direction if we want if we move, then we need only one node, only one edge to cover. So that's why this is the shortest path, and here it is 1. So in this way we will complete the matrix, and the highest value in the matrix will be the diameter of this particular graph. So here look, I have given one graph, and here total number of vertex are 13, total number of edges are 19, and I have calculated the cyclomatic number 7, alpha index 0.3, beta index 1.46, gamma index 0.57, and diameter is 5. So here In all case, cyclomatic number, alpha, beta, gamma, and diameter, higher the value and higher the connectivity of that particular graph. Now we'll be talking about the nodal connectivity or direct connectivity measurement. This direct connectivity or nodal connectivity is measured by connectivity matrix. The size of connectivity matrix involves a number of rows and cells equivalent to the number of nodes in the network. A connectivity matrix is always a square matrix. Suppose in a network has 5 nodes. Its connectivity matrix will be 5 by 5 grid. Connection. Each cell representing a connection between two nodes receive a value of 1. Non-connection. Each cell that doesn't represent a direct connection gets a value of 0. If all the connections in the network are bidirectional, that connectivity matrix is transposable. Adding of a row or a column gives the degree of a node, connectivity degree of node. The node having highest summation of connectivity is obviously the most connected comparatively to all other nodes. However, this assumption may not hold true on a complex network because of a large number of indirect paths which are not considered in the connectivity matrix. Local degree or road degree is sheer number of routes crossing or converging at a particular nodes. Usually, the summation of rows and columns of the direct connectivity matrix yields the local degree of nodes. Look here, this is the transport network, and that transport network is converted into graph, and here it is the connectivity matrix. As we saw earlier, the graph is composed of 13 vertex. Therefore, the connectivity matrix is composed of 13 by 13 grids. Look at node A. No edge is required to cover to reach A from A. Therefore, the value is 0. From A to B, A is directly connected with B. Therefore, the value is 1. Look, C is not directly connected with A. Therefore, the value is 0. D is directly connected with A, therefore the value is 1. E is not directly connected with A, therefore the value is 0. F is not directly connected, the value is 0. G, but G, look here, G is directly connected with A, therefore the value is 1. H is not directly connected with A. I is not directly connected with A, J is not directly connected with A, K is not directly connected with A, therefore the value are 0, 0, 0, 0. Look here, M is directly connected with A, therefore the value is 1. N is not directly connected, therefore the value is 0. In case of B, the same thing will do. B is directly connected with A, therefore the value is 1. B to B there is no edge, therefore it is 0. B to C, B is directly connected with C, therefore it is 1. B is not directly connected with D, E, F, G, H, I, J, K, therefore the value are 0. But M is again directly connected with B, therefore the value is 1. And N is not directly connected, therefore the value is 0, and so on. We will fill up for the matrix following the process. And then adding up the rows, this is the 4, and similarly this is 3, this is 2, 3 1 4 4 1 2 2 5 3. All those values we get. Now I'll show you how to map the connectivity matrix value. All the nodes are assigned to their respective connectivity matrix value, like A is 4, B is 3, C is 2, D is 4, and so on. Then we have to make a range. Here the highest value is 5 and the lowest value is 1. On the basis of the highest value and lowest value, we will find out a range. I have selected 2 and 4, and here the nodes having values less than 2 or equal to 2 will be separated by these isoplates. The isoplate is drawn here. This grid has value 2. This node has the value of 2. That's why here 2. Then it is 2 again. It is again 2. Then we'll draw the second isoplate of 4. In this graph, only one node, that is 5, have values more than 4. Therefore, this is the isoplate here. Look. Now, with the help of this isoplate map, we can prepare choroplate map also. The areas having lower connectivity matrix value can be shaded sparsely. The areas having moderate connectivity matrix value can be shaded moderately, and the areas having higher connectivity matrix value can be shaded densely. You can apply color also in the place of shade. Now we will talk about the interpretation, how to interpret. The node M is obviously the most connected since it has the highest summation, that is 5, of connectivity comparatively to all other nodes. On the other hand, nodes F and I are the lowest connected. However, this assumption may not hold true on a more complex network because of a larger number of indirect paths which are not considered in the connectivity matrix. Look at the range. Less than 2, the nodes are C, F, K, I, J, and these nodes are less connected, and A, B, D, E, G, H, N, all those nodes belongs to the group of 2 to 4, and these are moderately connected. And on the other hand, node M belongs to more than 4, and it is highly connected. So thank you.